let us start with the theory of the parabola. But before starting the theory of the parabola, let us understand what a conic section means and how the conic section's equations are derived and all. So, we'll study now. What do you mean by conic section? A conic or conic section are the curves corresponding to various plane sections of a right circular cone. This is a right circular cone which is shown in the diagram. Is of this form. This is cone when it is produced on the two sides is known as a right circular cone. So when we take a plane and cut them in different ways, the different types of curves are formed, in which we define it as a conic sections. And each point lying on these curves satisfies a special condition. That's why they're known as special terms called conic sections, which actually leads us to the mathematical definition of conic sections. So let us tell an English definition of conic section. English means in words. It means that if a point moves in a plane such that in a way that the ratio of its distance from a fixed point to its perpendicular distance from a fixed line always remains constant, it is known as a conic section. So one thing we will tell that the fixed point is called the focus, and the fixed line is called the directrix of the parabola, and the constant ratio is nothing but eccentricity, which is denoted by E. There are different values. For different values of E, there are different conics. Like for E equals to 1, it corresponds to parabola. E less than 1, it corresponds to ellipse. E greater than, it corresponds to hyperbola. Next, in this given diagram, the double right circular cone, which is the double cone, if we take a plane, and if the plane passes through the vertex of the double cone, then the equation, the curve which is produced, is nothing but a pair of straight lines. And if the plane makes an angle theta with the axis of the cone, which is this one, this is the theta angle between the axis and the plane, and the semi-vertical angle of the cone is alpha. This is the cone. This is not the semi-vertical angle. So if theta is less than alpha, we can say that two real and distinct lines are formed. That is because the plane cuts at two really, like this is the cone. If we take the half section of the cone, it will really cut the plane. If theta equals alpha, then it is on the circumference of the cone, like it is in this way, so only one line is formed. So both the lines are actually coincident. And if you take in such a direction, though it will not cut at all any points, so we can say that imaginary lines are formed. But the plane does not pass to vertex, and then the curve and intersection are known as the conic sections. Like if the theta equals to pi by 2, a circle is produced. See in this diagram, theta equals to pi by 2 and the circle is produced. If theta equals to alpha, means the angle is equals to semi-vertical angle, then a parabola is produced. So in this way. Next, if theta is greater than alpha, we can say that ellipse is produced in this way. And if theta is less than alpha, the plane cuts at two different points and two curves are produced, and the two curves comprises of a hyperbola. Next, mathematically, if you try to write that the distance of a point is from a fixed point and the perpendicular distance from a fixed line is in a constant ratio, to be of this form, if we assume the S as the focus, these are the directrix. So let's write them label them in our diagram. This is the focus. SP by PM equals to each is a constant. Next, let's assume a general equation for a conic. The general equation for a conic is actually ax square plus 2hxy plus by square plus 2gx plus 2fy plus c equals to 0. And there is a new quantity known as discriminant, which is defined as abc plus 2fgh minus af square minus vg square minus ch square equals to 0. And in case of the conic sections, the d is not equals to 0. Now, if d equals to 0, it represents a straight lines. Now, let's study about the parabola now. Parabola, it is the locus of a point which moves in such a way that its distance from a fixed point is always equal to the perpendicular distance from a fixed straight line, which means the E equals to 1. Here in the parabola, E equals to 1, and we'll assume that the standard equation of the parabola is obtained. When we assume the x-axis as the axis of the parabola, we'll study what are the axes of the parabola in the next theory part. This is the axis of the parabola, this is the focus, and we'll study that the parabola cuts the x and the y axis at origin. So this is the first part of the theory of parabola. Now study the second part of theory of parabola. So now we will define the terms. Now we'll first draw a parabola and then label them also for your convenience. So this is the focus. The axis is a straight line passing through the focus and perpendicular to the directrix, which is nothing but this is, in this case, is the x-axis in a standard parabola. Focus, we know that it is always in the interior of the parabola. Focal distance, we take any point on our parabola, its distance from the focus is known as the focal distance. Next, focal chord. You know that an infinite number of chords can be drawn in a conic section, but the chords which pass through focus are known as the focal chords. Now, the vertex, now we define it in a different manner. Now we'll assume different parabola, x square equals 4ay. Now if you try to plot the diagram, we'll get in this way. So you can say that the vertex of a parabola is the point the parabola crosses its axis. In our y square equals 4ax, it cuts the axis at this point, so this is the vertex of the parabola. But in this case, when the coefficient of the x square is positive, then the vertex is the lowest point on the graph. But in case it is negative, the vertex will be the highest point on the graph. Like if you take x square equals 4ay, the graph will be in this way. If you take x square equals to minus 4ay, the graph will be in the reverse direction. So we can say that in this case, the lowest point, if the coefficient of x square here is positive and here it is negative, actually we'll change it, it will become minus x square equals to 4ay. So here it is the highest point. So it is defined in another manner. In order to give a brief idea of this parabola x equals 4ay, the vertex is defined in this definition. Now we'll study what is directrix. We know that the directrix is the line from which the point has a fixed distance, the ratio we use in the eccentricity. But in another way, we can also say that a line perpendicular to the axis of symmetry is known as the directrix. In this case, our axis is also symmetric because the parabola is symmetric about the axis. So the directrix is the line which is perpendicular to that. Next, latus rectum. The latus rectum of a conic section is the chord through a focus but parallel to the conic section's directrix. In this manner, passing through focus. We know that focus is a we have to know that the focus in parabola is denoted by a, 0. Here we forgot to tell what is it. It is a, 0 in a standard form. Now latus rectum, the length of line, when we solve is x equals to a. So when we substitute this line in the parabola to find the points of intersection and find the distance, you will get it as 4a. It is the length of the latus rectum. The half the latus rectum is known as the semi-latus rectum. Next, any chord of the parabola which is perpendicular to the axis is called the double ordinate of the parabola. So we need to remember all these terms: directrix, latus rectum, double ordinate, etc. Now, as for all conics, in this conic also we will study the parametric equation. The parametric equation, one thing you have to understand is one quantity will be a parameter, and let us assume the parameter in case of parabola be t. So we will get the parametric equation of the parabola as at square, 280. We have defined this for our easiness, and this is for y square equals to 4ax. Now, let us study how to tell whether the given point is outside or on the parabola. So actually it's a parabola here, depending on S11. So in every conic, we have to understand that the position of a point is told with the equation of the parabola only, equation of the conic only. Here it is the conic is parabola, and it is given depending on the S11 value. And we know how to calculate S11 value from the circle chapter also. Again we will tell here, just for calculation of S11, replace the x and y terms by x1 and y1. So in this, the equation of parabola is y square minus 4ax equals to 0. On replacing y and x by y1 and x1, we get this equation. If it is greater than 0, it implies that the point is outside the parabola. If it is equals to 0, it implies that the point is on the parabola. If it's less than 0, it implies that the point is inside the parabola. Now, let us study some different conditions or special conditions which you might need to remember for the problem solving easiness. Like if you remember these conditions, you need not solve for these conditions again and directly use them in the questions. So the conditions is for a focal chord, if it touches 2 points, no? If it is a t1 square, 2a t1, like here the t is a parameter, so we can say that this point is p of t1. Similarly, if this has p of t2, then the t1 t2 is minus 1. If you take any focal chord and you determine the t1 t2, it will be minus 1. Next, now if we calculate the length of the focal chord, we'll get it to be a into t plus 1 by t whole square. And we know if we take a line, if it is the theta, so if we know that m equals to tan theta, and y square equals 4x is our parabola, and we know that here the slope of the tangent is given by dy by dx. If you differentiate and equate dy by dx by tan theta, and in the dy by dx, when you're substituting the points x1, x, y, you substitute at square, 2at. So we'll get the slope in terms of t. So when we substitute t equal the tan theta in t terms, then we'll get this equation, Fourier cosecant. You can derive that, or else you can directly remember the formula. We'll get the length of the focal chord as Fourier cosecant square theta. But we know from the trigonometry that the least value of cosecant theta is 1. So we can say that the least length of the focal chord is Fourier. Next, if you take a focal chord, then the focus divides it in 2 points, 2 segments. So if we assume that length is L1 and L2, we can say that, so we derive a condition that Fourier equals to 4L1 L2 by L1 plus L2. You can also remember this point. Now let us study the equations of tangents of the parabola. Now the point form of the tangent of the parabola is given by S1 equals to 0. We know how to calculate the S1. If it is x square term, replace it by x1, y square term, replace by y1. The x and y terms, replace 2x by x plus x1 and 2y by y plus y1. So in this case, our parabola is y square equals to 4ax. So replacing y square by y1 and 2a by x plus x1. So we'll get 2x by x plus x1, then we get this equation which is S1 equals to 0. And similarly, the parametric form, if you know how to calculate, how to derive the tangent equation from the equation of a parabola, like differentiate it, equate dy by dx equals to slope. Then we'll get this and substitute the point as 80 square comma 280. Then we'll get the equation as yt equals to x plus 80 square. You can also remember this. And if you solve the equations of the tangents at 2 points, p of t1 and p of t2, then they will intersect at a point whose coordinates are given by a t1 t2 comma 2a into t1 plus t2. Now let us study some important results on tangents of the parabola. If the tangent, if at any point, if we draw a normal and tangent both, if they intersect at t, p, then st equals to sg equals to sp. It's a very important property, you can remember that. Many of the questions might be based on that. Next, the portion of a tangent to a parabola cut off between the directrix and the curve subtends right angle focus. If this is the directrix, this point and this point subtend the right angle at the focus. You have to remember very importantly. It can be used in many problems. So all the points we will be studying now might be used in any of the question. Next, the tangents at the extremities of a focal chord intersect at right angles. So you might be thinking, actually you can say that these are the point of intersection of the perpendicular tangents. Yeah, it is true. And usually call the locus of the point of intersection of perpendicular tangents as the director circle. But in parabola, later when you study about the director circle, you'll understand it's nothing but a directrix. And it is a straight line, not a circle. Next, any tangent to a parabola and the perpendicular on it from the focus with the tangent at the vertex. So indirectly you can say that the locus of the feet of the perpendicular drawn from the focus upon any variable tangent is the tangent at the vertex. Now, if the tangent at P and Q meets in T, then the TP and TQ subtend right angle at the focus, like both the conditions are satisfied, then ST square equals to SP into SQ. The tangent and the normals at the extremities of the lateral septum of a parabola is the lateral septum, tangents and normals. Let us assume it's coming like this. Then they constitute a square and the point of intersections are minus a comma 0 and 3a comma 0. Actually we know 2 points are the endpoints of the lateral rectum. The other 2 points we have got now. So let's conclude the second part of the theory of parabola. We'll start the third part of the theory of parabola. Here we'll study another point. If we take the parabola, in that if it is the lateral rectum, and when on deriving we get that the length of the semilateral sectum of the parabola is nothing but the 2a is the harmonic mean between the segments of any focal chord. So if you take any focal chord, the length is constant for focal chord since we have studied, so the segments will be changing. So if the segments are b and c, we will study that the 2a equals to 2bc by b plus c, that the length of the semilateral sectum is the harmonic mean between the segments of the focal chord. Next, let us study about the normal, how to derive the equation and all. The point form, how to derive the equation. We know that the normal is perpendicular to the tangent. So if we calculate the slope of the tangent, so we can easily calculate the slope of the normal. So on solving, we get the point form of the normal as y minus y1 equals to minus y1 into x minus x1 by 2a. It is at the point x1 comma y1. Next, the parametric form of the normal to a parabola is given by y plus xt equals to 2at plus at cube. So it is a very important formula and we need to remember that. Next, we get a slope of the parabola as m, then we get the slope form. In the slope form, we'll get it as y equals to mx minus 2am minus am cube. Another important formula. And very important point, if you notice here, the equation of normal in a slope form is a cubic equation in m. So we can say that the maximum only 3 possible values are possible for real values are possible for m. So you can say that if you take any point, then a maximum of 3 normals are possible. 3 normals are possible from that point. So if we know any polynomial of degree n, so here it is degree 3. So if it is of this form, we know how to calculate the sum of the roots and the product of two roots, etc. So similarly here the cubic equation is in m. So if we calculate in that manner, you get the sum of the slopes as 0, sum of the product of two slopes as 2a by h, 2a minus h by a, 2a minus h whole divided by a. Next, then we'll, and all these conditions are only applicable. We assume that the normal passes to the point h comma k. It's a very important point we didn't mention above. And all these are applicable only when we assume like a common point h comma k. Next, the product of the slopes is given by minus k comma a. Why we have to assume this? This 2a minus h by a. Why we have to assume this is? So we'll assume because here these terms depend on the h comma k. That's the x and y coordinates of the point. So if the normals are drawn from different points, then these quantities also will differ in the value. Only this is constant, that if from any point we draw the normal, then sum of the slopes is 0. Important points are normals. Sum of slopes of 3 concurrent normals is 0. Next, the ordinates of the 3 co-normal points on the parabola is 0. What are co-normal points? If this is a parabola without 3 tangents, then these 3 points are known as the co-normal points. The center of the triangle formed by 3 co-normal points lies on the x-axis. These can be given in a question. Like they will directly tell they'll give 3 coordinates from which are the co-normal points, and they might ask what is the center of the triangle directly. So you have to remember that it will lie on the x-axis. So they will give the option in such a way that only one of the point given in the options lies on the x-axis. So we need to tick that. Or else you might be wondering how to take. Then you will take some case and solve. It will take a long time. So such points are important for such questions. Next, we'll study how to calculate the angle of intersection between two curves. One thing we have to understand is the angle of intersection between the two curves can be said as the angle between the tangents drawn at the point of intersection. We can only tell the angle between two curves when they intersect. So now we take two curves C1 and C2, and we know that if the two lines are with slopes m1 and m2, then the angle between them, if it is assumed psi, then tan psi equals to m1 minus m2 by 1 plus m1 m2. And we know that on derivating the curve, the dy by dx gives the slope of the tangent at that point. So we'll use the same concept here. We'll derive the slope of the tangent at that points m1. So for curve 1 it will be m1, curve 2 it will be m2. So on substituting the m1 as dy by dx at c1 and m2 as dy by dx at c2, we get this equation. So if we tell that the two curves are perpendicular, it means the tan psi is pi by 2, and we equate tan psi by 2, tan of pi by 2. Then we get this condition, the product of slopes is minus 1. If the angle is 0 or pi, the slopes are equal. Next, useful results in parabola. If the normal at 81 square, 281 meets the parabola, definitely that normal will meet again at another point, but at that point it is not the normal. That if it is p of t2, then t2 is given by minus t1 minus 2 by t1. Next, the tangent at one extremity of the focal chord of a parabola is parallel to the normal at the other end. We need to a very important point, it can be asked anywhere. Next, the normals at t1 and t2 intersect at 2a plus a into t1 square plus t2 square plus t1 t2 comma minus a into t1 t2 into t1 plus t2. This is important, you need to remember. If the normal at t1 and t2 intersect again on the parabola, then the condition is t1 t2 equals to 2. The normals will normally everywhere, two normals will almost intersect. Like if we take any two normals, they will definitely intersect at a point. But if they intersect on the parabola, this condition is applicable. And from this condition, we'll derive another condition that the normal at 2 points P and Q meet on the parabola, and the product of the ordinates of P and Q is 8a square. Next, if the normal chord subtends 90 degree at the vertex, like normal will pass through the parabola and will extend on the other sides also. So this is known as the normal chord, like the line between the endpoints. If it subtends 90 degree at the vertex, then t square equals to 2, and the normal chord of a parabola at a point whose ordinate and abscissa subtend 90 degree at the focus. So this is another point. Next, h. The normal at any point of a parabola is equally inclined to the focal distance and the axis of parabola. Now you're thinking, what is the focal distance? If this is a parabola, this is the normal, this is the focus. This the line joining the focus and the point is nothing but the focal distance. So the angle between the normal and the focal distance and the normal and the axis is same. So we need to remember that. Next, and we have already told what are the co-normal points. The points from which the normal drawn pass through the parabola is known as the co-normal points. Now we will study how to calculate the combined equation of the pair of tangents. From the x1, y1, if you want to calculate the combined equation of pair of tangents given by s1 square equals s into s1, we know how to derive s1, s and s11. And from here, these type of formulas are same for every conic, so you need not derive for all. Next, director circle. The locus of the point of intersection of the perpendicular tangents is called its director circle, and in parabola it's a straight line, not a circle. And small correction here, in this point G, the normal chord of a parabola at a point whose ordinate and both are same, like the x and y coordinates are same, then they subtend 90 degree at the focus. So there was a typing error here. So it means that the normal chord of a parabola at a point whose ordinates means x and y coordinates are same, then they subtend 90 degree at the focus. Sorry for the mistake. Next, the chord of contact. We know what is the chord of contact. The two tangents are drawn. The line joining those 2 points is known as the chord of contact. It's given by again s1 equals to 0. Next, chord bisected at a point. The equation of the chord bisected at a point p x1, y1 is given by s1 equals to s11. And again we know what is the diameter. The diameter is nothing but the locus of the midpoints of a system of parallel chords. And in case of parabola, its formula is y equals to 2a by m. Means m is the slope. So if we take this, we take normal chords. It is the slope of the chord is known as the m. We know that since they are parallel chords, all the slopes will be same for all the chords. So here it is given y equals to 2a by m. So let's conclude the third part of theory, the parabola here. Start the fourth part of theory of the parabola. Now we know what are the pole and polar from the circle chapter. So let us recollect them again. If we take any point and we can draw infinite secants, and the point of intersection of the tangent on the secants, the points where the secant cut the conic, is nothing but a straight line, and it's known as the polar, and that point is known as the pole, and the polar equation is again given by s1 equals to 0. Now we'll study some of the formulas which will make our calculations easy in some of the questions. So if we take a point p x1, y1, if we draw the tangent and subtangent, so tangent and normal, then they'll cut at points g and t. Now you might be thinking, what are the new terms, subtangent and subnormal? So we'll drop a perpendicular from that point on the x-axis, we'll cut at n. So the distance from that point to the point where the tangent cuts the x-axis is known as the length of subtangent. Similarly, the point where the normal cuts the x-axis and the point is known as the length of subnormal. So this is subnormal, subtangent. You can also say that it is the projection of the line of the tangent on the x-axis, and similarly the normal on the y-axis. Now the formulas on deriving, how we will derive the formulas. We know that the slope of the tangent is given by dy by dx, so dx by dy is nothing but 1 by m. So if we take this angle as psi and then derive the formulas using the trigonometry, we know that the pt is the length of the tangent, it's pn cosecant psi, and on replacing cosecant square as root over 1 plus cot square theta, cot theta equals to 1 by tan cot psi, and cot psi 1 by tan psi, and tan psi equals to dy by dx, we'll get these formulas. So we'll just recorrect them. Recorrect means we'll write in the other form. So the length of tangent is y1 into root over 1 plus 1 by m square. Similarly, the length of tangent is y1 into 1 plus m square. Length of subtangent is y1 by m, and length of subnormal is y1 into m. Now, there is an important property in a parabola, which means that, like in mirrors, you know that when a ray parallel to the axis strikes the mirror and passes to the focus of the mirror. So actually the mirrors are also a type of parabolas. So we can say that in a parabola, any line traveling parallel to the axis after reflection from the parabola passes to the foci of the parabola. So it can be said, asked in number of questions. We need to be careful and reviewing this point. So now we move on to the questions of the parabola. The questions will be quite easier. You just need to remember some of the formulas which will make our calculations easy. So let's start the questions.